I welcome Dr. Akio Kasuga. Dr. Akio Kasuga is an Executive Vice President and CTO of Sumitomo Mitsui Construction. He received his diploma and doctoral degree in civil engineering from Kyushu University in 1980 and 1997, the doctor's degree. He has designed more than 200 bridges and has experienced projects of research and development and construction sites and the construction sites. Dr. Akio Kasuga is Deputy President of AFRP from 2019 and to 2020. Incoming President January next year, 2021. And also he is the head of delegate of Japan National Member Group of FRB and a board member of Japan Prestressed Concrete Institute. We are waiting very much for the presentation of Dr. Akio Kasuga, a challenge to non-metallic bridges.
Today I will tell you the challenge of next generation's concrete bridges. So mainly my topic is a non-metallic bridge. It's a very long history from the beginning to the present. And also the final part of my presentation, I'll show you the non-metallic bridge with zero cement concrete. So everybody knows that what is different from Roman Pantheon and present concrete structures. So the Roman concrete is with no reinforcement, steel reinforcement. So the shape of the structure is only the dome and arch. But about 150 years ago in France, the reinforced concrete was invented. And also around 85 years ago, the prestressed concrete technology was invented too. But at the same time, we have the problem of the deterioration of the steel reinforcement, like photos by right-hand side. So the many engineers and researchers have been fighting this deterioration to solve the problem. So this is the roadmap of our long development of the non-metallic bridge. The first we started at the end of 90s. And at that time, we developed the bridges, non-metallic bridges for the Maghreb train. And we stopped during this area because of the cost. And also the new technologies have come, materials and structures. And finally, now we have been doing the joint research with the highway company. So this is the first generation non-metallic bridge from 1984. So I call this is the first generation. We built the private non-metallic bridge in 1990. And also we use some aramid fiber in marine structures and the pier strengthening. And I'll show you later we just confirmed the strength of the 28 years structures. But as I said before, we focused on aramid fiber reinforcement as a processing tendon in the concrete. This is a technology by Tochigi, Japanese company, which has very strong alkali resistance. So we chose this material instead of carbon. So at that time, the carbon aramid are available to use the new material in the concrete reinforcement. And we have concrete factories, and in the concrete factories we built the private bridges. One is pretension beams left-hand side, and another is post-tension beam right-hand side, which is 25 meters span, and the pretension beam is very short, around 10 meters. This is basically this technology is for the Maghreb, but as I told you later, we suspended this project because of the cost. So this is the photos of first generation metallic bridge, post-tension beam right hand side, and also pretension beam left hand side. In post-tension beam, we use the internal aramid fiber tendons and also external aramid fiber tendons. But reinforcement, we use epoxy coated rebar. So this is not exactly the non-metallic bridge, but we use aramid fiber. And in the center, our photo shows the non-metallic anchorage system by the glass fiber. And we measured by using the load cells for a long time. And at this moment, this system is very, very successful, and no damage observed at this moment. And for the pretension anchorage, we use a temporary steel anchorage system like this. It is very simple. We use a steel pipe, and also the inside of the steel pipe, we just grouted non-shrink mortar to get bond stress for the aramid fiber reinforcement. But this is temporary, and also we cannot use a couple of times. It uses only one time. And the pretension beam is completely non-metallic at this time. So we use aramid fiber tendons. At the same time, we use aramid rebars, longitudinally 8 millimeters, and also strap is the same. So this aramid fiber reinforcement is very, very expensive because we have bend it, and also we have very, very special manufacture before the construction. And at that time, the cost of these kind of non-metallic technologies 2 times of the usual initial cost of the prestressing beams. So we gave up to continue this first generation non-metallic bridge, and also this project was suspended at that moment. So after the stories, in 2080s, we cut one of the pretension beams, left-hand side, this one. This is 28 years old. And also we confirmed the strength of this short beam in our laboratories. It's a very, very simple bending test. And we confirmed that compared with the original design, the test results is almost the same, even it is 28 years old. So at the same time, the reinforced concrete and prestressed concrete, plastic material is very, very new, about 100 years. So we checked the durability, checked before the construction, and also this is a result. This is a fact that after around 30 years ago, all the new materials perform very well. So we have another 2 beams. I said, engineers, you should check in 2040, you should check in 2090. And also, instead of the old non-metallic bridge beam, as I told you the last part of my presentation, we built the new material, zero cement concrete plus aramid fiber reinforcement. This is the new generation's technology. So 2040 maybe I will arrive, but 2090 I don't know. No. So but up to 2090, so it's going to be then 100 years old. So we confirm the durability of the plastic fibers in 2090 by using a real model. Okay, after the suspending of the first generation, the new structure come, which is butterfly bridge from 2001. Oh, this helps a lot for the going to the next generation. So at that time, around 2000 years, we have very, very good materials, fiber reinforced concrete in the practical field. And also from 2000 up to 2013, we built the very, very new butterfly web structure, which leads to the lighter superstructure to reduce the concrete, because this kind of new concrete is expensive, more expensive than the ordinary concrete material. I'll show you the detail. In 1999, I drew the sketch like this. It is the conceptual design of a butterfly web. And also in 2001, it was patented only in Japan. And butterfly structure is the behavior is the same as the double wall truss like this. So the double wall truss, we built many composite structures, steel, diagonal, and concrete deck, but the force is concentrated on the node. So the node detail is very, very complicated. But instead of the truss diagonal, we just take the diagonal to the panel of the butterfly shape. So in the concrete, compression zone is okay, but tension zone we put in some prestressing tendons to reinforce the concrete structure. And also the horizontal shear force is distributed around the longitudinal direction. So the detail between this butterfly panel and concrete deck is not so complicated. After the concept of the butterfly wave, at that time, the first time the panel was steel. I presented in the paper 2006 in April Congress. At that time, the butterfly was steel. We did the test in 2003, and then we did a beam test in 2005. It's also the steel plate. But in 2006, we did the concrete panel. And also I presented in 2010 FID Congress in Washington, D.C. At that time, UHPC is available for the practical field. We checked the same things as a steel panel. This is a mixed proportion of the high performance concrete. And the strength, compressive strength is 80 MPa, not so high. It's not so special concrete base. And also this is a fiber. The tensile strength is more than 2000 Newton per square millimeters, which uses in UHPC. And also the content is only 0.5% in volume. The diameter of the fiber is 0.2, and also length is 22 millimeters. So this steel fiber comes from the fiber from radial tire. So this is also not so special materials. So we can procure anywhere in the world where the concrete tire factories are there. And also this is mixed proportion. We use 630 kilograms of cement. And as you know, there is not special material. In order to get the strength of the structure, we use the fiber, as I said before, and also pretensioning, post-tensioning, and the beam. This is a base, 400 plain concrete, and after the putting in the wire, steel wire, the strength is around 700. And also after the tensioning of the beam, the total strength of this structure is more than 1,000 compared with plain concrete, 2.5 times. So after that, we confirmed that this material can be used in the real structure. So the final confirmation point is the connection between the deck, the gap between the butterfly panel, so here and here. And to confirm the behavior by using the present specifications, we did a test by using a half-size model like this, the cantilever model. And this is a check of the design value, SLS, and also this is a dead load and ultimate. And this is the checkpoint of the specifications. So ultimate load is almost the same as the design value. So we confirm that we can use the present specifications in the connection point in these special technologies. So the next time is to use in the real structure. This is a Takubogawa Bridge, which awarded in FID, Outstanding Structure 2018, and completed in 2013. The maximum span length is 87.5 meters. And as you can see, the web thickness is only 15 centimeters. And also the butterfly panel is around, width is 3 meters and the height is around 3.5 meters. This is highway project. So the contractor like us should do the detailed design. So this is a basic design by the consultant, and this is detailed design by us. After applying the butterfly technologies, we can reduce the number of segments from 8 to 5 because of the lighter superstructure. And also each segment length is 6 meters. But the conventional ordinal box girder type, the length of segment is 3 to 4 meters. So this is the reason why we can reduce the number of segments 8 to 5, which means you can shorten the construction time. For the contractor, this is very happy. And this photo shows the butterfly panel was fabricated in our concrete factory beforehand. As you can see, inside of the butterfly panel, only the prestressed tendon is arranged, no reverse, in 15 centimeter thickness of the panel. And the two panels in 6 meter length segment arranged, installed like this. This panel is less than 4 tons. So at the construction site, we cannot change the heavy lifting equipment compared with ordinary box girder cast in situ type. So the reason why the construction cost is not increased compared with the cast in situ conventional ordinary construction way. Okay, this is the construction as usual. The free consolidation method completely the foam traveler is the same as ordinary box girder type. And the right hand side inside is unusual, very light. And especially the maintenance highway people are very happy because it is easy to inspect without no lightning device. So this means the maintenance is much easier than the conventional ordinary box girder. Okay, this is the photo after completion. After that, we are including under construction, have 6 butterfly bridges. This is a non-metallic butterfly bridges, and this is under construction. And this non-metallic bridge is completed in this year. Okay, this is a structure for the non-metallic second generation. After the development of the butterfly bridge, the second generation non-metallic bridge had come because the highway NEXCO West is one of the Japanese highway company announced us to have a joint research regarding non-metallic structure in 2010. We applied this announcement and we awarded to do the joint research. It's still continuing after the Bessodani Bridge 2020. Next step is the non-metallic precast slab. Okay, so the requirement of the joint research was the 1.5 times compared with the initial cost of the ordinary type of the bridges. And also at the same time, minimum life cost, which means almost no maintenance on the bridge structure itself. And the further difference from the first generation is the HPC, high performance concrete, is available, which leads to the non-river concrete, as shown in the later. And also this is a big difference from the first generation. And the second generation, this leads to the 1.5 times cost of these new technologies. So this is the outline of the non-metallic, second generation non-metallic, we call Dura-bridge. Precisely saying we use steel fiber, so it is not 100% non-metallic, but this is a short fiber, no problem in the concrete structure, quite different from the reinforcing bars. So the highway company allowed to use steel fiber. And also the tendon is aramid fiber. This is the same as first generation. We use this type of aramid deformed rod instead of the strand like this. Okay, the ordinary girder, we use steel reinforcement and also the steel prestressing tendons, but next generations we use aramid fiber tendons only. This is very simple and also no deterioration materials inside of concrete. Okay, in order to build the highway, which is box girder type, we confirm some points in the laboratories. So the fabrication of the non-metallic bridges, firstly the wear is fabricated, and after that the top slab and bottom slab is fabricated after the wear construction. So you can see here we have a pocket to connect with the top slab, and also this is the location. This is a place to connect to the horizontal ribs of the stiffened by ribs, stiffen the deck of the structure. So this detail is very important. We have to confirm the behavior of the long term. So this is a connection detail. We have a pocket here. We arrange the aramid fiber this way and this way and this way. And in order to confirm the fatigue durability, we use the cyclic loading here. And from 100 kilonewton to 200 to up to 300, about 4.5 million times. This is the result. So up to 4.5 million cycle was loaded, and no cracking and no opening of the joint is confirmed. And we confirmed that this detail is okay for the real structure. And also, a highway company asked us to confirm the fatigue test by using a foil running like this. And they have a regulation to check the durability of the slab from 150, 200, up to 300, about 500,000 times. From here, this is dry condition. From here, the wet condition is still needed to check the durability of this deck. So I hope this works well. This is a special test, and also this is equipment owned by the highway company. And after this is the result of the free running test. The deformation is the constant after the wet conditions. So finally, no crack, no opening of the joint, and no damage after this is equivalent to 100-year loading. So this is this new technologies. The performance is same as the conventional ordinary process concrete deck slab. So after that, we try to build in a pilot project. This is a temporary bridge for 2 years. The span length is only 14 meters, but every segment and also tendon size is the same as the real size. We check the behavior during the 2 years, and also we confirm the next step will be the real bridges in the highway. So this is Bessodani Bridge in Shikoku and the Tokushima Prefecture. It is a highway bridge, and the span length is only 26.5 meters. And just completed in this September. And there's a simple beam, and every segment was fabricated in our concrete factories. So the Bessodani Bridge is the first in the world as a highway non-metallic bridge. This is the construction, and each segment has less than 30 tons. This is a regulation of the Japanese transportation. And also you can see this is aramid tendons, no reinforcement inside of the butterfly panel. After this, we pour the fiber reinforced concrete. And this is the same as the pilot project. The butterfly part is constructed first, and also the bottom slab, top slab casting in the factory. Of course, we use non-metallic concrete barrier. In this case, we use a glass fiber rods to connect to the bridge deck. And each part are also fabricated in our concrete factories. You can see we have the AFRP levers like this and this one. We just injected the non-shrink mortar between the bridge deck and also the barrier. It is very easy to construct. But in this case, this concrete barrier is completely 100% non-metallic. Instead of the C fiber, we use a vinyl fiber because the concrete deck is a very, very severe condition. In Japan, we use de-icing salt during winter in the highway, so in order to avoid some small possibility of the deterioration, we completely remove this risk from the steel fiber to vinyl. And also, as I said before, the temporary prestressing for the pretension is only one use. It is one reason to cost higher than the conventional technique. So in this in this project, we developed the plastic wedge like this by, this is also co-development, joint development with a plastic company. But in this case, we use steel pipe, and also wedge is the plastic. But we can use this wedge about 10 times, and we can reduce the cost in this project. But now we are doing a development to develop the plastic female cone. But this is sort of difficult. But finally, we are focusing on the permanent plastic wedge and plastic female cones to anchor the plastic fiber in the future, near future. Okay, this is photos after completion. You can see that we have many aramid fibers, external tendons, because of the tendon size is very limited. And at the same time, we are developing now to the mulch type of the tendons by using strands. So in the future, the number of the external tendon is decreasing, I hope. As same as the Takubogawa Bridge, the inside of the box girder is very bright. We monitoring many things, and also you have to share the information with the highway company and us. Okay, so the next step now it's under designing. So we have many rehabilitation programs which were built in 60 years ago, from the reinforced concrete to the precast concrete. And the special case, we use a non-metallic deck like this, and also transverse direction and the longitudinal direction. The tendon is also, of course, the aramid fiber. And we have very small joint like this. And we already finished the wave running test with Express Highway Company. It's under design, and also the next year we will build this new type non-metallic slab, Dura-slab, in the west side of Japan, Chugoku Highway Expressway. Okay, so the final part, as I said at the beginning of my presentation, this is next technology with zero cement and aramid fiber, which means a non-metallic bridge with low carbon concrete. So this short beam, this is the depressed short beam, is zero cement and aramid fiber. We check the life cycle cost. In this case, is almost half of the ordinary concrete and ordinary steel reinforcement and the steel tendons. So this is the zero cement concrete is a very new material, and also compared with the ordinary concrete, we can reduce the CO2 up to 70%. So this is the characteristics of the zero cement concrete. Our concrete, we can get about 150 MPa, very high strength concrete without steam curing. And also at the same time, the dry shrinkage is extremely small, around 100 micro. And also the creep coefficient is about 1/3 compared with ordinary concrete. And also at the same time, the heat generation during hardening is about 30 to 40 degrees centigrade. This is much lower than the ordinary concrete. And also, as I said, CO2 emission can be reduced by up to 70% in a zero cement concrete type. Okay, so this is the CO2 emissions in around 70, 80 strengths. This is zero cement concrete compared with the normal cement. We have to reduce up to 70%. In the area of around 80, around 70, almost 50% we can reduce also. And at the same time, this concrete has very good characteristics. and ultra low shrinkage. And this is a shrinkage of the sustain concrete, zero cement concrete, and ordinary concrete. The strength is around 70. Now this is the dry shrink. Sorry. This is the dry shrinkage. This is autogeneous shrinkage. So compare with this type and this type, and also this type. The shrinkage is very, very low compared with ordinary concrete. And also the heat generation in summertime, the concrete rising up to around 70–80%, but by using zero cement, the temperature is less than 50. In the winter time, less than 30. So, which means the no cracking during hardening, and also no cracking during the curing, which means the high durability of the concrete, not only the CO2 emission. Okay, this is a concrete coefficient around 1/3, which means we can reduce the prestressing materials compared with normal type. Okay, let me conclude my presentation. To reduce future maintenance, non-metallic bridge was developed. New technology of butterfly web and rounded fiber reinforced tendons and fiber reinforced concrete. Fatigue performance of non-metallic deck is sufficient for more than 100 years service. This is the same as the present technology. Non-metallic technologies with zero cement concrete make the structures extremely durable and leads to the minimum life cycle cost. These low carbon technologies lead to sustainable solutions. So the final conclusion is my most important thing. We, as concrete designers, engineers, and researchers, should first pursue the low carbon technologies not only in materials but also in structures and construction and demolition. So after the pandemic, the world is dramatically changed, as you know. And also, as AFRP, we are heavy concrete user. And the cement industry themselves trying to reduce CO2 at the production process. But as a concrete user, we have to summarize, we have to launch, we have to present the low carbon technologies, not only the inside of the members, but also all over the world. So this is the next our mission through this very, very complex situation. Okay, so finally, the MPA concrete is a Portland cement, and the tendons is equal to the Roman concrete or not. Who knows? Thank you very much for your attention.
Thank you very much for your excellent presentation, including new types of bridge designs, application of non-metallic reinforcement, and the application of new types of concrete, zero cement concrete for the future. You have received a lot of messages and questions. I hope that we can have some of them, even if the time is just finished. Just a moment. So, for example, thank you for your response. Yes, okay. From the University of Belgium, Liège, Verdi, Robert Watley, were there concerns over the durability of the post-tensioning as the webs are open to the weather? So, a short question, but very important question. Yes. Were there any concerns?
Yes, you are right. But every external tendons are protected by using the present technologies, like it's the same as stay cable protection technologies. And if I show you the one program is the bird comes in the box girdle. This is quite different from the ordinal type. So the highway company do some measures to place the net in the opening, but there is no severe problem so far.
Yes, thank you. Jan Červenka, very nice presentation. Have you investigated the creep behavior of these butterfly segments? Does it have any impact on the loss of prestressing in these short prefabricated segments?
Okay, I tell you the non-metallic type. The aramid fiber, the elasticity modulus is very small than the carbon fiber. So the creep don't affect so much to the aramid fiber tendons. That's the reason why we use the aramid fiber tendons in the pretension parts, in transport direction and also strengthening of the butterfly web. So we of course we checked monitoring and the change of the stress of the aramid fiber, but no big change, and up to now it is the same as our expectation in design. Okay.
Yes, there is a question from Daria Memon. I give the abbreviated version of the question. It is easy to answer. I was wondering why CFRP, so carbon fiber reinforced polymer, was never used in your option.
Yeah. So now we are thinking about CFRP option, but as I said, this is a long history. At the beginning, we chose the aramid fiber, but now in Japan, the CFRP is available, and also the United States and all over the world. So we have to extend the use of the new material, not only the aramid fiber, to the CFRP. So yes, it will be coming soon. Okay.
Yes. Marco De Prisco, thank you very much for your very stimulating keynote. Yes, stimulating it was, but which is the difference between prestressed concrete, reinforced concrete bridges and this type of bridge in terms of ultimate limit states? So in ultimate.
Basically, I think there is no difference between reinforced concrete and prestressed concrete, and so I think it is the same in a model code.
A last question, because the time is running. We would be very glad to have many questions, and I also wanted to have some, but we have to start the break. So one question from China, Yu Zhang. Thanks for your impressive presentation. Will the torsion stiffness, the torsion stiffness be significantly weakened at the opening of the opening of section of the box girder? If so, what measures do you take? So this is torsion.
Yeah, it is very important thing. So I already checked the stiffness. Even the opening is 30% of the full wave type, but the torsional stiffness is not so weak, and also we have no problem in the Takubogawa Bridge is almost the straight bridge, but we don't have to have any experience of the curved bridge in the butterfly web. But basically, not big difference between the butterfly and the ordinary box girder.
Yes,
it's very strong.
So Akio Kasuga, thank you very much for your. Marco Di Pisco had write a stimulating presentation.
Yes, I will.
It's very much for the future, and it makes a lot of questions, and you did already a lot of answers. So
yes.
congratulations for the development on various fields, and we wish you a successful future in bridges and in FRB as well. Thank you very much.
Thank you very much.
Akio Kasuga. Thank you.